Today, we are going to talk about external flow. This is chapter 7 in your textbook. So, main objective of this chapter is try to estimate convective heat transfer coefficient from flow conditions and geometries. So in particular, we are going to see empirical equations or semi-empirical equations that will allow us to calculate H values for flat plate, cylinder, sphere, and tube banks. Okay. So before we go into details, I would like to talk about empirical methods. What does empirical method mean? So empirical equation means it relies on experience and observation without coming from a theory. Okay, so that's the definition of an empirical equation. So in general, when you are trying to set up empirical equation, what you need to do, you need to basically determine certain variables or parameters that are important for the problem. And then you vary these parameters and observe the outcome. And you basically you obtain correlations, the regressional analysis, and you obtain some equations based on input and output. Experimental setup for measuring convective heat transfer coefficient. So the basic elements of this setup is you have an electrical resistance here. You have an electrical resistance here. And you have a fluid at the velocity u infinity, temperature T infinity. It flows above the plate. So an initial temperature of the surface temperature of the plate is Ts, area is As. Since Ts is different from T infinity, so if we don't apply any electrical resistance, Ts will change. So what we are trying to do here, we have a feedback mechanism and we input voltage here, electrical resistance, to heat the system and to make sure that Ts remains the constant. So the power required to keep Ts constant is basically heat transfer rate. And then based on the surface area and temperature difference, and after you have Q, you can basically calculate H sub L. So that is the idea behind this empirical or experimental setup for measuring convective heat transfer coefficient. Again, also we want to make sure that the electrical power generated within the system is not going to dissipate away from the system, so there is an insulation. So the heat transfer is only occurring on the top where we have the convection. So this is the experimental setup, and various experiments have been done, and see how does the heat transfer coefficient depends on other variables. So these experiments are done in terms of dimensionless variables. So one of these dimensionless numbers is Reynolds number, and if you plot log Reynolds number versus log Nusselt number, and you'll see you get a straight line. So that means you have a power law dependence. So that means the slope is prime number. And if you do the similar experiment, if you want to narrow it down, if you plot Nusselt number over prime number to the n, you get a straight line, and this is Reynolds number. Okay, so this equation tells us the average Nusselt number, this indicates average here, over bar indicates average, is a function of Reynolds number and function of Prandtl number, and this is a power law relationship. So here it again, Nusselt number, average Nusselt number is function of Reynolds number and Prandtl number. Reynolds number is evaluated for the whole plate at the distance L. And the definition of Nusselt number, we saw this in chapter 6. The convective heat transfer coefficient H, L is the length of the plate, Kf is the fluid thermal conductivity, and Reynolds number is obviously velocity times length over kinematic viscosity, and Prandtl number is kinematic viscosity over alpha. Okay. So before we move on, just the main idea here. So Nusselt number is basically telling us h. So h is a function of velocity, right? If you want to think about it in simpler terms, so Reynolds number contains the velocity, and h is basically what we are trying to do. So basically in this case h bar. H bar is what we are trying to calculate based on the flow condition. Obviously, flow condition is oversimplification. So we have multiple properties here. We have viscosity, thermal conductivity. So all of these properties depend on temperature, obviously. So temperature also changes these variables. Okay.